All right, thank you, Thomas.
Okay, all right, thanks. So let me just introduce you again. So the next talk is going to be given by Martin Roetteler from Microsoft. He's going to tell us about Azure Quantum.
Thank you, Thomas. And let me just begin by saying it's really good to be back at QIP. This is personally, I think, my 8th time I'm at QIP. My first one was at a time when it wasn't even called QIP. It was called AQIP, I think, in 1998. And if you go back to that time, if you reflect on what quantum computing was like, it's kind of crazy how the field developed over time. Back then, if you wanted to do any kind of experiment with a quantum device, you better be friends with people like Raymond Laflamme or Rainer Blood or Yasunobu Nakamura and go to the lab, collaborate with them, wear safety goggles. And like that was very difficult actually to get even access to good devices. If you fast forward 25 years to now, we are seeing this incredible revolution where quantum clouds are emerging, basically democratizing the access to the devices. Everybody on the planet can, in principle, get access to the devices. So at Microsoft, we're obsessing on kind of the next step, like how can we make it even easier for people to get access? How can we open it to more languages, more platforms? And how can we kind of help people to really like bankroll their operations by providing credit programs? I'm going to show you all of that and also give you a little teaser of what kind of research you'll be able to do with our platform. So just as an overview, slide is not advancing well. There you go. Just as an overview, let me unpack that slide. The slide shows the typical software development process for quantum applications. So what you're seeing is like the phase from let's kind of build the algorithm, let's try to express it in a quantum programming language, which involves a choice on the developer side, namely what language to choose from. And then the next thing is like how to integrate it with a classical compute. There's typically a choice to be made as well. And then you write your tests, you start developing small prototypes, you start simulating them, emulating them, apply resource estimation frameworks. It's very important actually to make sure that your code is correct. And then finally you hit the device when you run it. At Microsoft, we have the principle of we're really open in terms of the languages. One of the philosophies is we want to support any language and any platform. That comes really from our dev div. They have that same mentality, same mindset. So in concrete terms, that means we're supporting Qiskit, we're supporting Cirq, we're supporting Q#. Basically, any language that you can code in, it runs on our platform. It goes even further. Like if you're even kind of broader than that, and you don't work with any of those languages, but you have code that can be sent to the APIs of our hardware partners, we have so-called pass-throughs that allow you to bypass all the languages, everything, and directly send it through Azure. You can send those payloads to the hardware providers. So that gives developers an incredible choice and opportunity to directly access the hardware. So there's the language. Then you have the classical frameworks. A lot of Python frameworks are supported. There's a support for the .NET frameworks, which is also great for enterprise developers. And then finally, on the test development side, there's a lot of simulators we expose. I'm personally very excited about a sparse simulator that we recently developed. It's right now in a preview stage, but that allows you to go way beyond 100 qubits by exploiting sparsity of the wave function. And that sounds like, oh, wait, when I'm really sparse, if I run a random circuit, it's not sparse in general. But it turns out in many applications, actually, you have very sparse states. Think about implementation of Shor's algorithm, where you use certain encodings in terms of coset states, typically very sparse. Chemistry is sparse by physics or by chemistry, by selection rules. And so in many of those cases, you can go over 100 qubits. Isn't that cool? And we have open system simulators. And then you hit the devices. And so right now we have 2 platforms that are supported. They're by Quantinuum, which is an ion trap platform, and IonQ, which is an ion trap platform that you hear a little bit more in the following talk. We're also on track to expose Rigetti, which is a supercomputing superconducting platform, and QCI, another superconducting platform, and there's more to come down in the pipeline. So there's this incredible ecosystem. Let me show you how it looks like, what the experience like to actually sign up. It's very easy, a few clicks, and you can create a so-called workspace. You can select your providers, and then they get populated in your workspace. What's really nice is it's already coming for free with a credit program. So they're like per hardware provider, let's say IonQ or Continuum, you already have $500 in terms of free credits. So you can work through those $500 and spend them and get an initial idea what it's like actually to work with this platform. That is the stuff you can do today. It allows you to work with near-term devices. And I want to show you also what you will be able to do tomorrow in terms of the tools. So tomorrow, to get ready for tomorrow, Microsoft is honored to be part of an alliance, really, of several participants that have a common goal, namely to develop an intermediate representation for quantum programs. So quantum programs typically go from a high level of abstraction all the way down to the hardware, to the bare metal. But immediately, you will have to rewrite your program, you have to apply optimizations, and this is a very complex task with many facets. So we want to have tools that reduce the development effort, that reuse as much as possible in terms of existing compiler technology, also make you future-proof for further developments in the field. So there's this alliance called QIR, and you can see here the members, QCI, Rigetti, Oak Ridge, Continuum, and Microsoft are part of it today, but it's expanding and ever growing. There are more partners going to be added in the future, and it's very active. So what does it actually even mean, like QIR? How can I think about it? So as you can see here on the slide, you have this enormous diversity in terms of programming languages and frameworks, right? There's Q# that we're very passionate about at Microsoft because it allows very nice high-level programming. There's Qiskit and OpenChasm, Cirq. QCore is the Oak Ridge framework that already couples to many other languages and testbeds internally. You have Zapata's platform, very many languages, and also many backends, many hardware backends. So if you were to now devise a binding or like an interface between all these frameworks, basically from N languages and K backends, you have to develop N times K interfaces. It's a pretty daunting task. If you go through an intermediate representation, you compile it into that, and then you target the backends, you only have to do N plus K interfaces, which still is a lot, but much better than having all the combinations between the interfaces. Plus, it gives you opportunity to optimize at that level. QIR is based on a programming framework called LLVM that's very active. Like if you compile today, for instance, a C program using a standard compiler, very likely you go through an intermediate representation like LLVM. It has a ton of rewrite steps built in, a ton of optimizers that have been implemented in form of compiler passes. So as QIR is based on that, all of that can be imported. It already comes with all of these compiler passes. And then we're building these backends that allow you to specifically target all this hardware. And what's really, really cool is it unlocks hybrid compute. You hear a lot about hybrid compute these days. The way we think about it is it should be really fine-grained, classical, quantum, hybrid computation in a way that ultimately even has like, there should not even be a boundary between classical and quantum. So we want to be able to express that. And then as the hardware matures, we want to be able to go with the hardware and support this kind of hybrid programming framework. I want to make this very real for you guys here, because I know that you're researchers and you want to know what can I actually one day do with hybrid. So let's pick an example. Let's pick just good old phase estimation. Let's say we want to do a phase estimation, ground state estimation of a simple molecule, for instance, with your Hamiltonian. You do phase estimation, or you can do variational methods, right? VQE versus QPE. So what are the differences? What are the advantages? So if you go down a VQE path, obviously the advantage is you have very low depth circuits, right? And that can be mapped to many existing hardware. Of course, the downside is typically your shot counts are quite high. It scales like if you aim at a target accuracy of epsilon, you typically have to do 1/epsilon square many experiments to get into that ballpark, right? So it's a clear downside. Contrast that with phase estimation, you don't have that limit of the shots. In fact, it's Heisenberg limit that it's like, oh, 1/epsilon is your limit there. But of course, your circuits are very deep. typically, right? It scales like you have to do your control U, control U square, and so on. Very deep circuits. So by going to hybrid algorithms for phase estimation, there are actually trade-offs that kind of allow you to trade off resources like the classical compute side versus the circuit depth. So there are methods that actually can pick kind of the benefits from both worlds, have low depth, and at the same time are Heisenberg bound only. So it's like O of 1 over epsilon in terms of sample size. And these methods typically involve an adaptive choice of your next measurement while your state is coherent. Okay, that's very hard. And kind of think of it like this. There are typically some models, like in your model, there are typically some parameters that you want to estimate. You then pick the next kind of quantum program that you want to run based on the current state, which let's say it's a variance and a mean, describing your model. Then depending on the current setting, you pick your next round of phase estimation, right? Involving the next power of your operator, involving a phase correction and whatnot. And then you run that against your state, you get an outcome measurement, outcome say 0 or 1. Depending on it, you update your model, you get new model parameters. And then typically, like in the standard flow, you just then go back and you re-prepare your state and so on. You really get much more power if you can stay coherent while you made that update and then keep updating that state you have. It's known, there's work by Cassandra Grenade, Nathan Weeb. They show that in principle, it gives you more power, you learn more. And in particular, you can adapt to noise models by doing that. So kind of the system learns how to adapt against this model. And this is, the importance here is that this update, this is basically a fixed point operation. Okay, so, but it's a non-trivial operation where you multiply two numbers and you add numbers. All of that stuff happens while the system is coherent. So QIR allows you to do these kind of operations. And here's some data that we got from running a QIR program on QCI's hardware. That's the superconducting computing startup I mentioned in the beginning. And what you can see in that case, there was a single Z rotation. It had an eigenvalue of 0.5. So as you can see, indeed the maximum is at 0.5, but there's of course some spread because of noise. But the system learned what that ideal eigenvalue is and did a few iterations, stayed coherent along the way. Okay, so I want to close by reminding you, kind of, you can sign up and try the Azure Quantum for free today. There's already a credit program, $500 for everyone. We also have, for, if that's not enough, for research purposes, we have a $10,000 credit program. It's very, very kind of low touch. You send in a very simple proposal. It's just a few paragraphs. And then it gets reviewed. And in many cases, we have funded those projects. You get access to a very diverse set of quantum hardware. And that really allows you to explore kind of quantum algorithms and write them today and make them so that you can run them in the future. Thank you very much for your attention.
Martin, so we have time for questions.
Hi, I'm not sure I fully understood what you were demonstrating there, but is it right to say that you were doing conditional circuit operations on measurements? So you maintain, you perform some kind of measurement, you maintain coherence, and then you do a conditioned circuit operation on what you measured.
Great question. So the question is it really conditional operations we do here based on earlier rounds of the experiment? That's correct, yes. To confirm, like the model kind of gets updated, and based on the current state of the model, we do the next operation. So that could involve stuff like selecting the next power. In the standard, like Kitaev style phase estimation, it's all predetermined, right? You go basically through control U, you control U square, U to the 4, you go through all those, gather the results and post-process. Here, that's not predetermined. So in order, you can think of it like this, in order to kind of unroll this, there's something like, if you do 20 rounds, like 2 to the 20 possible experiments that you could do, and you will only take one trace through those 2 to the 20. And that, like, if you were to store it as a table lookup, would be a gigantic amount of data to even store all these possible runs. The one you select is based on the earlier measurement, so you only take basically one trace.
Yeah,
does that help? Or?
Yeah. So which device is that taking place on?
It's a device by QCI. It's a relatively small device still. Like for that run, for instance, we needed, I think, only 2 or 3 qubits. but they have a roadmap for their devices that I would love for them to speak. I cannot comment on our hardware partners, but they're one of our partner hardware in Azure Quantum.
And is that the only piece of hardware that has that functionality, or do any of the others?
There's a plethora of hardware providers that have that in their roadmap. It's actually quite exciting to see that like this hybrid concepts, they are emerging, and several like hardware providers have this vision, including Quantinuum, for instance, and several others. They also have this vision of having like unlocking really truly hybrid compute. And that's of course useful for error correction, but there are many other things at the algorithm level that also tremendously benefit from hybrid compute. I could go on here, but there's several examples that really have been shown by researchers over time.
Quantinuum has hardware with circuit vision as well as
Okay,
that's cool.
There was just a call out in the audience, a person saying that Quantinuum also has this ability of doing mid-circuit measurement and operations.
If anyone knows of any other hardware that has that functionality, I'd be very curious to hear. So
yeah,
thanks.
Sure. Thank you for the question.
Hi, thanks for the nice talk. Regarding the intermediate representation, one thing we heard from Dave Bacon earlier today is that people have to do various tricks that are specific to particular quantum computing platforms and chips and really, really detailed things. Can an intermediate representation capture some of those special things that have to happen, or is it just going to sort of abstract away all of that?
Yeah, great question. The question is like kind of what tricks, what kind of techniques does an intermediate representation actually unlock for the algorithm developer? Actually, there's right now we see a trend that naturally gravitates towards having more capabilities for developers. And you can see it as certain levels of capabilities. Like lowest level would be just a bare circuit followed by measurement, which already takes you very far, I would say. This is kind of, when I think about algorithms, most of the time I think of that capability. The next level would be sort of allowing some kind of batch processing. And that's, I'm sure Dave was talking about that in his presentation, that kind of it kind of allows to do iterative methods like VQE or QAOA in a way that's supported, so you don't have to wait too long for the result to come back. For that to happen, though, you must have some sort of proximity of the classical and the quantum compute, maybe a co-located device that sits near the quantum device. But what I'm talking about here is going even further. This is going kind of to a state where you are so tightly integrated that you can, while the device is coherent, do some classical compute. That in turn kind of offers more optimization and more compute capabilities. I hope that kind of answers the question. I'm not sure.
It was useful.
Thank you.
Let's take one last question. Yeah.
Hi, great talk. So I'm wondering, in the example you gave about the classical quantum sort of alternating aspect, right? So but why do I need to go to the intermediate representation in that case? Because so maybe it's a two-part question. So where do you envision that the classical processing is happening? Is it, for example, like something like some cryo-CMOS which is sitting and whatever, generating some an updated pulse to generate the next circuit? And if it is something like that, then why do I need the intermediate representation in this example?
The question is, why do we need it in the first place? Why do we need QIR in the first place? How does that kind of dovetail with architectural decisions that we might need to make when we build a quantum computer, if I understand your question correctly? So my take on this is that kind of, there are certainly things on the kind of control side that you do not want to express even in terms of QIR. Things that are very close to the device may or may not be good to express it in QIR. Like think of it, for instance, the error correction logic itself that we need to make it fault tolerant. Probably that's not an example of what we want to express in QIR and run it, even though we could also think of proof of principle at that level. The way I think about it is more like kind of what is the kind of way to express even a classical piece and a quantum piece in a way that a compiler can use to rewrite. And then ultimately the compiler can even make the decision how to host this. Like what's the right level? Like I can do my classical optimizations, my quantum optimizations, but it might be then still a choice there, like how to mix and match, what operations to choose from which library and how to bring these things together. So those are things that ultimately, hopefully, really powerful compilers can do. Right now, oftentimes humans do it by hand optimizing kind of the libraries or kind of which ones to choose. But still, there's this kind of, you need that capability at some level to even program the device, to express it that you want this operation to happen while the quantum state is coherent. So that's one of the ideas behind QIR, to unlock that and to have one framework that's already founded in classical technology that like LLVM has a lot of, like it has a 25-year plus history of providing these rewrites.
Thank you.
Thank you. Great question.
Okay, let's thank Martin again. Thank you.